Have you ever wondered if there's a center of the universe? Well, it turns out there's not. The universe, despite its mind-boggling vastness, lacks a central point. Let's start at the beginning. Around 13.7 billion years ago, the Big Bang happened, but contrary to what you might think, the Big Bang wasn't an explosion from a specific central location. Instead, the universe began as an incredibly compact and tiny state. From that moment, every point in the universe started expanding uniformly. And guess what? It's still expanding today, so there's no single central point in the universe. To help you visualize this, imagine a two-dimensional ant living on the surface of a perfectly spherical balloon. For the ant, every point on the balloon's surface looks the same. There's no center or edge. As you inflate the balloon, the dots on the surface move away from each other. Similarly, galaxies in our universe are moving away from each other. The ant doesn't know about the third dimension inside the balloon, just like we can't perceive dimensions beyond our three-dimensional universe. Our universe is like that ant's two-dimensional balloon world, but in three dimensions. However, the balloon analogy represents a finite universe, and cosmologists aren't sure if that applies to our own universe. Our observations are limited by the distance light has traveled since the Big Bang. The entire universe might be infinite. If so, we can imagine it as an infinite, flat, expanding rubber sheet, or even an unbounded loaf of raisin bread, with each raisin representing galaxies moving away from each other. In this infinite scenario, there's no central point. Studying the large-scale structure of the universe is truly fascinating. Here are some key methods. These surveys, like the Sloan Digital Sky Survey, provide insights into galaxy clustering, positions, and velocities. Analyzing the redshift of light from distant galaxies helps scientists infer their recession velocities. Hubble's law relates redshift to distance, creating a cosmic distance ladder. Cosmic microwave background is the afterglow of the Big Bang. Measuring its temperature fluctuations reveals early universe patterns, including density variations that seeded galaxy formation. Supercomputers simulate the evolution of cosmic structures, predicting how galaxies cluster over time. These subtle density fluctuations help constrain cosmological parameters by creating a preferred scale in galaxy distribution. Scientists construct 3D maps of galaxy positions, revealing cosmic filaments, voids, and superclusters. These structures trace the underlying cosmic web. Filaments, vast tendrils of galaxies, connect cosmic voids, forming the skeleton of the universe. Observations of type Ia supernovae measure cosmic distances and provide clues about the universe's expansion rate. Topological studies. Researchers explore the universe's topology, whether it's finite or infinite. Poincare dodecahedral space and other exotic possibilities are considered. While the concept of a centerless universe is intriguing, our understanding is limited to what we can observe, the observable universe. This cosmic horizon is defined by the distance light has traveled since the Big Bang, around 13.8 billion years ago. But because the universe is expanding, the observable radius is actually about 46.5 billion light years. It's like looking back in time, seeing the universe as it was, not as it is. Imagine standing on a vast plain that stretches infinitely in all directions. Your view is limited by the curvature of the Earth, creating a horizon. Similarly, our cosmic horizon limits our view of the universe. Beyond it lies the unobservable, forever hidden from us by the speed of light and the universe's relentless expansion. The observable universe is a treasure trove of wonders. Beyond our familiar Milky Way lies a vast cosmic expanse teeming with galaxies. Let's explore some of them, large and small Magellanic Clouds. These are the closest galaxies visible to the naked eye. They appear as fuzzy patches in the southern sky. The Large Magellanic Cloud is about 179,000 light-years away, while the Small Magellanic Cloud is closer. Andromeda Galaxy, M31. Our nearest spiral neighbor, Andromeda, is a majestic galaxy about 2.537 million light-years away. It's on a collision course with the Milky Way, destined for a cosmic tango billions of years from now. Triangulum Galaxy, MM33. Another member of our local group, Triangulum, is a smaller spiral galaxy located about 3 million light-years away. It graces our northern skies. Sagittarius Dwarf Elliptical Galaxy. This dwarf galaxy orbits the Milky Way and is approximately 70,000 light-years distant. It's a faint companion, often obscured by dust clouds. Maffei Y and Maffei 2. Discovered through infrared emissions, these galaxies lie nearly in the plane of the Milky Way. They're elusive, tucked behind our galactic disk. But there's more to the universe than just galaxies. At the heart of some of these galaxies lie active galactic nuclei, AGN, emitting substantial energy across the electromagnetic spectrum. Unlike star-produced luminosity, AGNs exhibit non-stellar emissions in radio waves, microwaves, infrared, visible light, ultraviolet, X-rays and gamma rays. These intense sources of radiation likely stem from matter accreting onto a supermassive black hole at the galaxy's center. AGNs serve as cosmic beacons, revealing distant objects and constraining models of the cosmos. The most potent AGNs are known as quasars, while blazars are AGNs with Earth-directed jets, their radiation amplified by relativistic beaming. A supermassive black hole, SMBH, is the largest type of black hole, with a mass on the order of hundreds of thousands to billions of times that of the Sun, M. These cosmic behemoths reside at the centers of most massive galaxies. Here are some key points about them. Size and mass. SMBHs typically have masses exceeding 100,000 solar masses, M, and some reach several billion M. Their gravitational pull is immense. Event horizon. Unlike stellar mass black holes, the tidal forces near an SMBH's event horizon are weaker. You wouldn't feel significant tidal forces until deep within it. Galactic influence. Almost every large galaxy hosts an SMBH at its core. For instance, our Milky Way has one called Sagittarius A*, powering AGNs. Accretion of interstellar gas onto SMBHs fuels active galactic nuclei, AGNs, and quasars, releasing prodigious energy. The history of our understanding of the universe is a captivating journey that spans millennia. Greek and Indian philosophers, ancient thinkers proposed geocentric models, placing Earth at the center of the cosmos. Ptolemy's geocentric system dominated for centuries, Copernicus and heliocentrism. In the 16th century, Nicholas Copernicus revolutionized cosmology by introducing the heliocentric model with the Sun at the center of our solar system. The Big Bang model, around 13.7 billion years ago, the universe began as an incredibly hot, dense point, a singularity. This event, known as the Big Bang, marked the birth of space, time, and matter. Cosmic inflation. A fraction of a second after the Big Bang, the universe expanded faster than light during a period called cosmic inflation. Its cause remains mysterious, but it explains features like the universe's flatness and large-scale structures. Nucleosynthesis. Within minutes of the Big Bang, protons and neutrons collided, forming the earliest elements: hydrogen, helium, and traces of lithium and beryllium. The universe was still too hot for complete atom formation. Epoch of recombination. Around 380,000 years after the Big Bang, the universe cooled enough for atomic nuclei to capture electrons. This epoch of recombination cleared the cosmic fog, making the universe transparent. Light could now travel freely, revealing the cosmic background radiation. The afterglow of the Big Bang. Formation of cosmic structures. Over billions of years, gravity acted on tiny density fluctuations left by inflation. These grew into galaxies, clusters, and cosmic filaments. Galaxy formation gas collapsed into proto-galactic clouds, igniting star formation. Supermassive black holes formed at galactic centers. Cosmic web. The universe's large-scale structure resembles a web of filaments connecting vast voids. These filaments house galaxies and galaxy clusters. Observations and discoveries. Cosmic microwave background, CMB. In the 1960s, the discovery of the CMB by Arno Penzias and Robert Wilson provided strong evidence for the Big Bang. Hubble's law. Edwin Hubble's observations of galaxy redshifts revealed the universe's expansion, dark energy and dark matter. Recent discoveries highlight the mysterious components: dark energy driving cosmic acceleration and dark matter shaping galactic structures. Modern cosmology, inflationary cosmology, inflation remains a central idea explaining the universe's large-scale properties. Cosmic Microwave Background Explorer, COBE, Wilkinson Microwave Anisotropy Probe, WMAP, and Planck Satellite. These missions refined our understanding of the CMB and cosmic parameters. From ancient cosmologies to modern discoveries, our journey through the universe's history not only reveals the cosmos, but also our insatiable curiosity to understand it.